Hi guys, welcome to another lecture in the series Organic Chemistry 1. And today we're going to be talking about select reactions and preparations of alkenes and alkynes, as well as other functional groups. Now, for alkenes, you should have known that they consist of sp2 hybridized covalent bonds, right? And for their synthesis, you would have been introduced to them already. That is the hydrogenation of alkynes using which catalyst? So that should ring a bell. Which catalyst? Metal reduction of alkynes. And which alkene is formed? Is it cis or trans? And you'd have also looked at the dehydration of alcohols, you know, your E1 and your E2, which would have led to an alkene, as well as your dehydrohalogenation of alkyl halides. So in other words, we remove our hydrogen and the halogen and we end up with an alkene. So all of these methods you would have been introduced to prior to this. Now, for the synthesis of alkynes, these are, somewhat similar types of reaction, particularly the dehydrohalogenation we just mentioned for the alkenes. Now, it just happens twice to form an alkyne. Now, removal of two molecules of HX, as I was saying, from a vicinal or geminal dihalide produces an alkyne. And just in case you don't remember what is the difference between vicinal and geminal, just pointing out here that this is a vicinal dihalide. That means the halide or the halogen, they're beside each other in a 1-2 relationship. As opposed to a geminal dihalide, the halogens, both halogens would be on the same carbon, all right? So it could be either the vicinal or the geminal dihalide can produce removal of them can produce a alkyne. All right, so the first step is easy and it forms a vinyl halide. And then the second step, you have another removal of a hydrogen halide from the vinyl halide, and it requires a very strong base and very high temperatures. All right. So here we have the base, sodium amide, and the vicinal dihalide, and we remove two molecules of HX, so X being bromine here, and we form our alkyne. Now for the mechanism, we see here for step 1, the base will pull a proton, and as we can see, it's an E2 mechanism, so therefore it is concerted. So the base will pull a proton, then we form our double bond, and then the halogen will be eliminated. And that is why this is a dehydrohalogenation. All right, so we end up with our vinyl halide seen here, right? So that just means that we have a carbon-carbon double bond, and we have the halide attached to one of the carbons. Now, the second step is the difficult step, and so a very strong base is definitely needed for the second step, because clearly there's a stronger bond between this carbon and the hydrogen, and therefore it essentially will need more power to pull this proton. All right, so the sodium amide works fine. It will pull the proton, form or triple bond, and then remove the halogen using the E2 mechanism again. And in this case, we end up with our triple bond. So notice here that the angle is 180 degrees, right? So this is how you draw your triple bond. So we remove 2 molecules of HX as we have seen here. So moving on to addition reaction. So we're going to show how we add to an alkene. So firstly, we're going to show addition of HX, right? So most of the times, you know, through your organic chemistry career, when you see X, usually it refers to a halogen, no? So alkenes react as Lewis bases in the presence of strong mineral acids. And so HX, that's our mineral acid, to generate the more stable carbocation. So this leads to substitution of X at the more substituted carbocation. So if you recall your Markovnikov addition, yes, that's what we're talking about here. The more stable carbocation will be generated. So as I said, the more highly substituted carbocations are generally more stable. And as you know already, right? Because here we're talking about primary, secondary, and tertiary carbocation. And you know that the tertiary would be more stable than the primary, for example. So the proximity to a heteroatom or an increase in the number of resonance contributors will increase the stability of the carbocation. So by this stage, we understand what resonance contributors are, and the fact that we can have an increased number of resonance contributors, and that will cause an increase in stability of the carbocation. We know this already. So if rearrangement can occur to yield a more stable carbocation, that carbocation is assumed to rearrange. So of course, we know about our 1,2 hydride shift or our 1,2 methyl shift. All right, so let's show an example here, right? So we have our alkene, and to that we're adding our mineral acid, which is hydrogen chloride or hydrochloric acid as we know it as. So our double bond here is being nucleophilic. It can abstract our proton for more acid, breaking our hydrogen chloride bond, as is evidenced by the arrow starting here and ending on the chloride. And so I hope it's clear to you that the positive charge can be on this carbon or this carbon. And we know the rules which govern which one is preferentially formed, right? So here we see a secondary cation, which is less stable than our tertiary cation, right? So this tertiary carbocation is more stable and it will form preferentially. Once that happens, our chloride ion, which was eliminated in the first step, can now attack our positive center to end up with, in this case, 2-chloro-2-methylbutane. All right, so this is an example of addition of HX to an alkene. All right, but what if we had a rearrangement, such as, 1,2 hydride shift, as we mentioned before, and as you're already familiar with, right? So let's see. So we have our double bond here, or alkene, and in the presence of a mineral acid again, it can be nucleophilic to attack our proton, breaking our hydrogen bromide bond. And so the electrons will now end up on the bromine, forming a bromide ion. And so here again, we see the possibility of the plus charge ending up on either of the carbons, right? So we either get a secondary carbocation or a primary carbocation. So we can see here that, if we have to choose between primary and secondary, clearly the secondary will form preferentially. All right. And so the point we're making here is that if a rearrangement is possible, which it is possible here because we have a neighboring hydrogen, and if we have a 1,2 hydride shift, we will move into a more stable arrangement. That is, we'll be moving to a more stable carbocation. Then that rearrangement will definitely happen. So here we would have had a secondary carbocation, 1,2 hydride shift. So this hydrogen moves to the adjacent carbon, and now the carbocation is now a tertiary carbocation. So we have moved from a secondary carbocation to a tertiary carbocation via a 1,2 hydride shift. And of course, our bromide will attack our positive center, and then we end up with our alkyl halide. So the step that actually did not happen would have been the bromide ion attacking the secondary carbocation here, right? So that is a possibility. However, it did not happen because this reaction happens fast and is favorable because you're moving to a more stable arrangement. So a 3-bromo-3-methyl pentane, which is this one, is the major product. The rearrangement of 5 to 6, that is 5 to 6, must be faster than the reaction of bromide ion and 5, right? So we're saying that this must happen quickly in comparison to the bromide ion attacking the secondary carbocation to give the second product. In other words, K2 must be faster than K4. So the rate of this reaction must be faster than the rate of this reaction, which is not favorable. So in a similar fashion, we can demonstrate the rearrangement in this case, a 1,2 methyl shift, right? So similar type of thing, right? So we have our hydrogen halide here, or double bond being nucleophilic as usual, abstracting our proton, and we have the possibility of forming a primary or a secondary carbocation. Clearly, the secondary carbocation is favorable. And because we have a neighboring methyl, that methyl can shift to the adjacent carbon, thereby resulting in a tertiary, more stable carbocation. And of course, our halogen is just ready to attack our positive tertiary carbocation to form our alkyl halide. So in carbocation rearrangements, the migration must occur on adjacent atoms. So it must be a 1,2 arrangement, okay? So 1,3 or 1,4 migrations will not be observed, right? So 1,2, as we saw with the hydride shift, it's always the adjacent, the one beside it, right? So just remember that. All right, so the other reaction of alkenes that we'll be looking at is the formation of our halohydrins, right? So this should ring a bell as well. So we have our alkene here, we have our halogen, and we have water. And in the presence of all of this, we have the addition of a chloride ion or chlorine here, and hydroxyl group here. So if chlorine or bromine is added in the presence of water, then the major product obtained is a halohydrin, right? So we would recall the halogenation of alkenes, how that work, right? Without water. So some time ago, we would have spoken about, for example, the bromination of an alkene, right? So we form more bromonium 3-membered ring, and then the bromonium ion would have attacked, and so we end up with a 1,2 dibromo product. Rings a bell? Well, it's a similar mechanism here. However, because there is water, and in this case, alcohol can do the job as well. So it's a similar mechanism where you would have had the formation of the 3-member bromonium ion, or in this case, the chlorine ion here. And then you would have attack of water. Instead of the bromide or the chloride ion, you'd have attack of water. So let me just do that quickly so that you can follow what I'm saying here. So I'm speaking about this 3-membered ring, right? So let's say we have already bypassed the attack of the double bond, right? And now we have our bromonium ion or the chlorine, whichever, right? And then we would have had water being nucleophilic, attacking from the back side, as they would call it. And that is why we end up with a trans arrangement here. So the halogen is usually on the other face compared to what is being added. All right, so once water is added, then the next step would have been to remove one of the hydrogen, and therefore this is called a halohydrin. So looking at this here, we can have attack of an alcohol as well. So it doesn't have to be water as we just saw. It can be an alcohol. So it says here, the attack of water is always at the more positive because it resembles the more stable carbocation, the more substituted carbon atom, right? So this is for unsymmetrical amine. So clearly it doesn't matter here, right? But there are cases where it matters because this alkene is unsymmetrical. So we're saying if we have an unsymmetrical alkene and the possibility exists for the carbocation to be formed at either, we're saying the more stable carbocation would be generated. And so the methanol or the alcohol will add to this carbon in preference to the other. All right, so let me just repeat that. In the example that we looked at the previous slide, that was a symmetrical alkene. Now here we have an unsymmetrical alkene, and the water and methanol are behaving the same way, right? So clearly it would have been the oxygen of the methanol that would have been behaving like water, right? So we're saying here that the attack of water or alcohol is always at the more positive center, right? So here, this is the bromonium ion that would have been the intermediate, and so the point is we could attack either here or here, and we're showing the different resonance structures here, but this is our intermediate, and we're saying that the alcohol or water will attack this carbon as opposed to this one, and that is because that is the more positive and it resembles the more stable carbocation. So that leads us to question 1, which says, suggest reagents and conditions as well as a mechanism for the following reaction, right? So we have essentially the same molecule. So this is just an exercise to go through. All right, so we have our symmetrical alkene here, and we need to figure out what reagents and conditions will affect this product. And so this is what we're saying happens, right? So we have our chlorine, right? Because clearly the final product has chlorine and the methoxy, right? So the first thing that you want to do is to analyze your product, right? What is in your product that is not in your starting material? So if we look closely at our products, we would recognize that we have a halogen and we have a methoxy. So that should tell us immediately that our reagents are chlorine and methanol. So it's an alcohol or water, remember that. And so we add to our or alkene, right? So we're already familiar with this reaction here, where we see that our alkene is being nucleophilic, and clearly our bond or halogen is polarized by association with our alkene. So we form our three-membered ring, which is strained, right? And so our methoxy ion from our methanol can attack our carbon here, breaking our carbon chlorine bond to quench positive charge, and so end up with the product seen here. Now, you might be wondering, why did you draw the ion versus the alcohol? So we could have done that as well. We could have drawn our alcohol instead, and then the product of that would have been our and then we could have another molecule of methanol pulling that proton and quenching that positive charge, right? So the whole point of this is that we have a trans stereochemistry, right? So because of the attack, so the attack of our methanol is from the back side, and therefore that results in our trans product seen here. So our follow-up question 1 is, suggest a mechanism for the formation of an alkyne from a geminal dihalide. So the third reaction that we're going to look at is epoxidation, right? And so that's, let's just draw the epoxide, right? So that three-membered ring there. So a single oxygen atom is added to a carbon-carbon double bond to make an epoxide. And so the oxygen is provided a per carboxylic acid or per acid, and these per carboxylic acids can be made from any carboxylic acid by replacing the OH with OOH. So we're familiar with our functional group carboxylic acid, and we're saying that for per acid it will be like that, right? So not that, but that. And so this reaction occurs due to the weakness of the oxygen-oxygen single bond of the per acid. That is this single bond here. And so these are two per acids, right? So we have per acetic acid. So if we recall, the structure of acetic acid, which is CH3, and so our per acid just inserts another oxygen, and the other one will be new to you, may be new to you. So it's M-chloroperbenzoic acid, and we call it MCPBA for short. And so I hope you recognize here that you have a meta relationship between the carboxylic acid and the chlorine here, which is why you have a M-chloro per, it would have been benzoic acid had it been a carboxylic acid, and because it has the extra oxygen, it is now a per benzoic acid. So it's M-chloroperbenzoic acid, and you will see sometimes MCPBA for short. And what they do is, in the presence, the alkene in the presence of these per acids will form epoxides. So the mechanism looks something like this, right? So we have our per acid here, and then there's a reaction between our oxygen, this bond, oxygen hydrogen bond, and or oxygen and the double bond, right? So that is how we form the 3-membered ring between the oxygen and these two carbons here, right? And while that is happening, you know, we're forming a double bond is now being formed between this carbon and oxygen. So this oxygen bond, as we said, is weak, and so it will break to form a double bond here. One of these bonds are broken to pick up our hydrogen here, right? So that's how we end up with our carboxylic acid and or epoxide. Now, as you would recall, in the labeling experiment that was done here as well, and so labeling experiments replacing the natural isotope 16 with the less abundant isotope 18 shows that the oxygen atom of the epoxide comes from the OH oxygen in the peroxy acid. So they labeled the oxygen with the less abundant isotope oxygen 18, and when they analyzed the product, they found that that was the oxygen that made up the epoxide, and therefore that would have guided or confirmed the mechanism. So just another example here of cyclopentene with our per acid. So in a similar fashion, you know, there's this bond breaking and bond forming between the both carbons and the oxygen. This bond, this oxygen bond is being broken, as we saw up here as well, right? So this bond is being broken to form the double bond here. One of these bonds is being broken to pick up this proton here, and so we end up with our carboxylic acid and or epoxide. What's interesting to note here is that the the reaction of a halohydrin with base results in the formation of an epoxide as well. So if we know how to make halohydrin, which we know now, right? We can react that with base in order to form an epoxide as well. And this is the mechanism for adding base to an intramolecular SN2 reaction forming the epoxide. So this is simple because we know what bases do. Bases will abstract a proton, right? So it will pull this proton here to form our oxide ion, which can then attack our electrophilic center here, because clearly this carbon halogen bond would be polarized as a result of the halogen being attached to it, right? And so once the base pulls a proton, the oxide can be nucleophilic, attacking our electropositive or electrophilic center here, and then causing our carbon bromine bond to break to form our epoxide. And note the inversion which happened at this carbon. All right, so another reaction that we're looking at is oxidative cleavage, and you would have been familiar with the term ozonolysis, right? Ozone, yes, and cleavage, yes, right? So we are familiar with ozone. We know about the ozone layer, right? So that's 3 oxygens, and they are bonded in a fashion seen here, and clearly these are resonance structures, so the electrons are delocalized across all 3 oxygens, right? And so in the presence of an alkene, which we see here, right, the expected product was, this species here. However, what was observed was the cleavage reaction via a ozonoid. So clearly the carbon-carbon bond broke. So this is what they expected. However, the carbon-carbon bond broke in the process. So both the sigma bond and the pi bond of the carbon-carbon double bond unit in the alkene have been cleaved, as we see here, right? So the carbons are no longer bonded to each other in a sequence of reactions. So we see here that rearrangement occurs to form the ozonoid, and this is not usually isolated. So it's postulated, but it hasn't been isolated. So just to mention the reagents here, nonetheless, the ozone is used in the first step to reach the ozonoid, and then you have hydrogen peroxide being used in the second step to effect the products. So this is just another example of the ozonolysis reaction. So we have our alkene here in the presence of ozone. The first step perhaps is what we would have expected. However, the carbon-carbon bond breaks, and there is a rearrangement to form the ozonoid seen here. And then the key point to note here is that, on this previous slide, we saw the workup being hydrogen peroxide, and then we end up with 2 ketones, right? And here we're seeing a variety of products because we have 2 different workups, right? So we have an oxidative workup in the form of hydrogen peroxide, and we have a reductive workup in the form of zinc HCl, or the sulfur dimethyl sulfide seen here, right? So this is the reductive workup, and the product will vary depending on which workup ends the process. All right, so let's look at it a little more. So for let's appreciate where the bond breaks first. So that is our cleavage, right? So for the reductive workup, literally this is what happens, right? So if we just insert an oxygen where the double bond is, then we will end up with the 2 products. Do you see that? So that is our reductive workup. For oxidative workup, one of the products varies, or is different, sorry. So for our oxidative workup, the same bond is cleaved. However, and let me just redraw my double bond down here. So the same bond is cleaved. However, for the oxidative workup, there's an extra oxygen, right? So we end up with where the line is, we end up with 2 oxygens, and then we end up with an extra oxygen where there is a hydrogen. I hope I haven't confused you, but the point I'm making here, we can have 2 different workups with ozonolysis. We can have an oxidative workup and we can have a reductive workup, and these are the reagents that will affect a reductive workup, right? And so the cleavage reaction happens in both, but the products are different. So for the reductive workup, as we see, we just imagine that we insert 2 oxygens here and we get the product, right? But for the oxidative workup, that happens as well, but there's an extra oxygen where you have a hydrogen attached to this carbon seen here. And you know, you might be wondering, what is the biological relevance of all this that we're doing? Well, the reactions of alkenes with weak acids, example water, the hydration reaction, is known in biological system. You might be familiar with the Krebs cycle from biology, the citric acid cycle, and it's important for the metabolism of most aerobic cells. And one step in this cycle converts fumarate to malate, seen here. So we actually have an alkene that is hydrated here in the presence of an enzyme called fumarase, and the enzymatic conversion is a trans addition of water. So these reactions that we're talking about here, they are very, very relevant because they occur in your body. All right, so that leads us now to question 2, which says, give the products of the following reaction. So again, we have our alkene, but this time we have ozone and the workup is zinc in acid, right? So just take a second and try to come up with the product of this reaction. All right, so if you actually drew this, then you would have been correct, right? So it was very important for me to number my carbons. So a lot of people get confused with this. You must account for all carbons. This is a 5-membered ring, and the cleavage would have happened there, right? And this is a reductive workup. So we would have ended with 2 aldehydes here, and then we just have 1, 2, 3 carbons in between. So 1, 2, 3 carbons in between our aldehydes. So our follow-up question 2 says, give the products of the products of the following reaction. So an alkene in the presence of MCPBA, what is the product that you would expect for that reaction? So now we're going to talk about the addition reactions of alkynes. So let's see what happens here. So for the addition of HX, right, so we have our alkyne here, and in the presence of acid, you know, this triple bond will be nucleophilic, and the hydrogen will be added to one carbon So clearly it is symmetrical, right? So that it doesn't really matter. So the hydrogen will add to one carbon, and then the positive charge will be on the other carbon. So from then, our halogen can attack from either side of the double bond. Right, so this is a vinyl cation. So anytime you have a plus charge on a carbon that's a part of a double bond, it's a vinyl cation. So we can add to either side. The bromide can add to either side of a double bond, leaving the product seen here. And just to note that these vinyl cations are indeed unstable. All right, so continuing with the addition of HX, the vinyl cation is linear because the carbon atom is sp hybridized, as we know, and with an empty p orbital. And it can be attacked by bromide ion from either side, as we saw, resulting in the formation of both E and Z alkene products. So you'll have a mixture of E and Z alkene products. The instability of the vinyl cation intermediate means the alkynes react more slowly with electrophiles than do alkenes. So the alkyne that we just looked at was actually symmetrical. So it didn't really matter which carbon the plus charge ended upon. However, let's look at this example where the alkyne is not symmetrical. And so as usual, you know, it being nucleophilic, adding our hydrogen, breaking our hydrogen chloride bond to form our vinyl cation here. And we can see where the cation can either be on this carbon or the other one. So either carbocation 17 or vinyl cation 18, right? And so we're seeing here that the one that will form will be 17 as opposed to 18, right? And so the vinyl carbocation 17 is more stable than the primary vinyl 18. It forms fast and leads to the major product. And a point to note here is that vinyl carbocations, they do not rearrange, right? So here we're comparing the primary versus the secondary vinyl carbocation, and again we're consistent here that the secondary vinyl cation will form preferentially, and then you'll have attack of your halide to form or product seen here. All right, so the addition of a second mole of HBr to the alkene generally gives the geminal dibromide. The intermediate carbocation is stabilized by interaction with the lone pair of electrons from the bromine. Right, so the reaction can happen twice in essence, right? So we can add another molecule of HBr here, and the reaction will happen in a similar fashion as we have seen several times before now, right? Addition of the acid to the double bond. And in this case, the geminal dibromide will be the major product as compared to the vicinal dibromide. And as we said, that is because the carbocation that would have been generated, this one would have been more stable. And that is why the geminal dibromide is favored. So here we're looking at hydration. hydration of alkynes, right? So hydration of an alkyne will generate an enol which tautomerizes to a ketone in most cases. So what is the reagent for this? Well, you just need water, some sulfuric acid, and mercury sulfate. So for the first step of the mechanism, it involves the formation of the enol. So as usual, when we see a term, we like to break it down. So enol. So this is the enol. So the en is the alkene portion and the ol, the alcohol, right? So enol. So our first step involves the addition of the hydrogen, right? So clearly this is the hydronium ion which will liberate its proton, right? Because it's acidic. So our vinyl carbocation would have been generated here and the hydrogen added to one of the carbons. And clearly it is a secondary vinyl carbocation that is formed, and water can now be, because we have water in the system, it will attack our positive vinyl carbocation, and so we end up with this intermediate species, and then we can have another molecule of water abstracting the proton to quench the positive charge to end up with our enol. So that's the first step of our hydration of our alkyne. First, we generate an enol. This enol tautomerizes in step 2. So what is ketoenol tautomerization? Well, it's just a rearrangement of sorts, right? And so we have our enol, and our pair of electrons on our alcohol moiety can form or double bond, which would result in this double bond abstracting a proton from the hydronium ion, and water can now pull this proton, and therefore this hydrogen oxygen bond can be broken to quench a positive charge on the oxygen to form our ketone, right? So that's why it is called ketoenol tautomerization, because it's transforming from an enol to a ketone, as we see here. So firstly, you have protonation of the carbon, that is this carbon, and then you have deprotonation of the oxygen, which results in our ketone formation. So here, and as usual, as you would have seen, that a lot of the times we compare symmetrical versus unsymmetrical species. This is no different. So here we're looking at the unsymmetrical alkynes. So an internal alkyne seen here, and if it undergoes, well, in the presence of, remember what we have, water, sulfuric acid, and mercury sulfate, right? We'll have hydration. And essentially what we're seeing here is that you can get a mixture of products. So you can have the ketone on, or the carbonyl, sorry, on this carbon, as well as you can have the carbonyl on this carbon. However, when you have a terminal alkyne, and that means an alkyne at the end of the structure, in the presence of the same reagents, you end up with a methyl ketone. So a methyl here and a ketone here, right? So an internal alkyne, you get a mixture. If it's the alkyne is in the middle, you get a mixture of the carbonyl being on this carbon as well as this carbon. However, if it's a terminal alkyne, you get a methyl ketone exclusively. And the third reaction we're going to be looking at is hydroboration. And so when you have a pi bond of an alkene and it's reacting with our borine to give an alkyl borine, where the boron is attached to the less substituted carbon atom of the carbon-carbon double bond unit, right? So here we have our double bond, right? And then in the presence of our borine, we can have the boron being attached to the less substituted carbon of the unit, right? So clearly we have a double bond and we have a methyl, so one is more substituted than the other. So the boron will attach to the one that is less substituted. That's what we're saying. And so alkynes are expected to react similarly, but the presence of the second pi bond of the alkyne will lead to a vinyl borane product rather than an alkyl borane, as we see here. All right, so let's look at the products of the reaction when we react borane with our terminal alkyne here, right? So we will form an alkyl borane or vinyl borane as we see here. And in the presence of hydrogen peroxide and base, we will form enol, which will then tautomerize to our aldehyde as the major product. So this is the minor product here. And as you have seen, the boron attaches to the less substituted carbon here, and clearly that is why this is the minor product here. So it attaches to the less substituted carbon, and then in the presence of peroxide, hydrogen peroxide and base, we form our enol, which can be converted to an aldehyde, which is the major product. So the ketone is, this methyl ketone is the minor product here. So hydroboration of a terminal alkyne leads to an aldehyde as the major product. The enol intermediate is actually not isolated. So they just speculate that it must have gone through that intermediate in order to lead to the aldehyde. And this is the mechanism for this reaction seen here. So as we said before, the boron will attach itself to the least substituted carbon, and the hydrogen will add to the other one in the presence of the hydrogen peroxide and base. We have formation of the enol, and then the enol tautomerizes to our aldehyde. So in comparing the hydration of terminal alkynes, right? So if we compare hydroboration oxidation, it converts terminal alkynes to aldehydes, as we just saw, because addition of water is non-Markovnikov. As opposed to the mercury 2 catalyzed hydration, it converts terminal alkynes to methyl ketones. So just a comparison here, that if you see a difference in the product, then you will know which reagent will give you the particular product if you react it with a terminal alkyne. All right, so that leads us now to question 3, which says, give the product or products of the following reaction. So what you will do here is you'll inspect your substrate, right? Is it a terminal alkyne or not? And we have all the reagents here that we have just seen a while ago, and it's a terminal alkyne. So this is a no-brainer here, guys, that we have an alkyne, an aldehyde that would have been generated here. And since we started off with 3 carbons, then we must end up with 3 carbons. And our follow-up question 3 says, give the product or products of the following reaction. So again, we have an alkyne with mercury sulfate, sulfuric acid, and water. So please tell me the result of that. All right, so now we're going to look at select reactions and preparations of alkyl halides. All right, so we are familiar with our alkyl halides, and we know that they are compounds having a halogen attached directly to the carbon of an alkyl group, right? So as we said before, the X, when we see it in organic chemistry, it's usually referred to some halogen, and it's formed by the overlap of our sp3 hybridized carbon orbital with our halogen orbital. And the bond angle here is near 109 degrees, and therefore the structure assumes a tetrahedral geometry. So how do you prepare these alkyl halides? Well, via free radical halogenation of alkanes, which we saw, or it could be addition of hydrogen halide to a carbon-carbon multiple bond, whether it be Markovnikov or anti-Markovnikov, which we have seen, or it could be nucleophilic substitution of alcohols, which you may not have seen. So you definitely would have seen these two. All right, so here we're looking at the nucleophilic substitution of alcohols, right, as one way in which we prepare our alkyl halides, since we're already familiar with the other 2 methods, right? So here we have alcohol, and we have various halogenated species here. Potassium tribromide, potassium pentachloride, HCl, etc., right? Thionyl chloride. And we are replacing our alcohol, or substituting, I should say, our alcohol with our halogen seen here. So throughout the course of our study, we have seen the C reaction several times, and so we'll be looking particularly at A, B, and D. All right, so just to be clear about, I'm not sure if I've been saying potassium or phosphorus, but whatever it is, I'm saying thionyl chloride, HCl, phosphorus pentachloride, and phosphorus tribromide, right? All right, so reaction of alcohols with PBr3 for short, right? And so we have alcohol, and it's a very intuitive mechanism here. And so our oxygen will be nucleophilic, and it will attack our phosphorus, and then that will cause our PBr bond to break. And so we end up with this species, this intermediate here, and then our bromide ion that was displaced up here can attack our electrophilic center, causing our carbon oxygen bond to break, and you have inversion of the stereochemistry. So here we see that the reaction results in an inversion of the stereochemistry, as well as we have 2 halogens left here on this species, which can undertake the reaction 3 times in total, right? So we just did replacement of 1 of the halogen here, so we can actually replace the other two, essentially, right? And so here we see the formation of our alkyl halide from an alcohol with phosphorus tribromide. So the primary and secondary alcohols, they react with phosphorus tribromide, PBr3, to yield alkyl bromides, as we just saw. The reaction does not include the formation of a carbocation and therefore usually occurs without rearrangement of the carbon skeleton, especially if the reaction is kept below 0 degrees Celsius. And the reaction occurs in 2 steps. So first we have the attack of the alcohol on the phosphorus, and then the bromide displaces this species, which is a good leaving group. And with regards to the reaction of alcohols with hydrogen halides, the arrow shows the increase in reactivity of alcohols towards hydrogen halides. So our tertiary alcohols, they're most reactive, while our methyl and primary are the least reactive towards our hydrogen halides. So this is a reaction that we know already, right? So just to refresh our memories, we have our alcohol that is protonated, resulting in our hydronium ion here, and we have a very good leaving group in the form of water, which we can break our carbon-oxygen bond to quench positive charge on the water. And so we end up with a tertiary carbocation, which is very stable. And then we have the halogen, which can attack our positive center to end up with our halide here. And that's for tertiary alcohols. So for primary alcohols, the SN2 pathway dominates. And so in a similar fashion, well, this would be more concerted. And so the oxygen will be protonated and therefore will liberate our halogen, which will now attack our electrophilic center, and the carbon-oxygen bond will break, quenching the positive charge on the water to end up with our alkyl halide. And then finally, our reaction of alcohols with thionyl chloride, it converts primary and secondary alcohols to alkyl chloride. And pyridine is often used to promote the reaction. So the absence of pyridine in the reaction results in the retention of configuration. So here we have an alcohol, and we have thionyl chloride with pyridine here and without pyridine. So in the absence of pyridine, we have retention of configuration, while in the presence of pyridine, you have inversion of configuration, as we see here. All right. So the pyridine is very important to control whether or not you want inversion or retention of your chiral center at your chiral center. All right, so let's look at some reactions of alkyl halides. So I mean, we're all familiar with all of these here. For primary alkyl halides, usually SN2 or E2, substitution or elimination, and E2 happens with bulky base only, For our secondary alkyl halides, we also have SN2 as well as E2 with a strong base, and SN1 is also possible, and E1 if we have a weak base or weak nucleophile. And for tertiary alkyl halides, E2 can happen with strong base. However, we see SN1 and E1 happening with weak base or nucleophile. So alkyl halides is one of those very important functional groups because they allow us to do functional group transformations in the form of SN2 reactions. So in an organic synthesis, because they're able to convert one functional group to other, they are very important. And so these reactions always occur with inversion of configuration at the carbon that bears the leaving group. So here we have a plethora of reactions of alkyl halide. So our alkyl halide is here in the middle, right? And we have, notice here that these are all nucleophile, negatively charged species, right? And so if we have a SN2 reaction and it's a primary or secondary halide, then we can have a SN2 reaction, right? So we can react it with a halogen, cyano group, thio, oxides, methoxide, etc., or hydroxide, even or deprotonated alkyne. All of these reactions are possible. So we see here, right? We start off with the alkyl halide, but we can end up with a thiol sulfide, an ether, an alcohol, etc., ester, other halides. So we can see here that, alkyl halides is very important to organic chemistry. And just to mention our vinylic and phenyl halides, however, so our vinylic halide is the halide that's attached to a carbon that's a part of a double bond, while our phenyl halide, obviously, right? And so our vinylic and phenyl halides are generally unreactive in SN1 and SN2 reactions. And so for SN1, the vinylic and phenyl cations are unstable and do not form readily. For SN2, their carbon halogen bonds are so much stronger than that of the alkyl halides, and so the electrons of the double bond or benzene ring repel the incoming nucleophile. So it's a different ball game with vinylic and phenyl halides. So now we're looking at select reactions and preparations of alcohols and ethers, which is our final section. All right, so alcohols, and we can see several reactions here of our alcohols, and some of them you're familiar with, or most of them. So alcohols, we know that they're higher boiling point than comparable ethers or hydrocarbons. They associate with each other through hydrogen bonding. Ethers have solubility in water, which are similar to alcohols of the same molecular weight. And the solubility of alcohols in water gradually decreases as the hydrogen chain lengthens. So that should make sense as well. As we increase the carbon, we decrease the water solubility. So we know that already. All right, just to look briefly at this image here. So we have a secondary alcohol here, and this is showing how we can make it essentially from aldehyde and a Grignard reagent, or alkyl halide, which we just spoke about. In the presence of an alcohol, we can form a secondary alcohol or ester. Hydrolyzing an ester, we can get back the alcohol. Various reactions here. So another reaction that you would have been introduced to would have been oxymercuration, demercuration. And it sounds fancy, but really it's just a reaction here for alkene with mercury acetate, and the first step is called the oxymercuration, and then the second step, which involves sodium borohydride and base and water, involves demercuration or removal of the mercury acetate to form our alcohol. So this is one way in which alcohol can be synthesized. So we're going to look briefly at the mechanism of this reaction, and it should be familiar to or bromination of alkene mechanism. So in a similar fashion, the same thing happens with our halogen, right? To form the three-membered ring, the water comes in, attacks our carbon, breaking our carbon-mercury bond, or water now abstracts our proton, and we therefore quench positive charge, and then you have a removal of the mercury with sodium borohydride to form our alcohol. So from our alkene to our alcohol here. So there are several reactions of alcohols that I'm sure you're familiar with a number of them. So you're familiar with your esterification, maybe the formation of ethers, reduction, substitution, definitely oxidation, and definitely dehydration to form alkenes. So let's look at the reduction of alcohols. So first is, A, dehydrate with consulfuric acid followed by hydrogenation to form an alkane. So this is we know this reaction already, right? The alcohol is protonated, it leaves, and then we have an elimination reaction essentially to form our alkene, and the alkene, in the presence of hydrogen and metal catalyst, we end up with an alkane. Now this reaction may be new. The tosylate followed by a reduction of lithium aluminum hydride. So we have our tosyl chloride here, which can replace our hydrogen here, right, to form our tosylate, and this species can be reduced by lithium aluminum hydride to our alkene, right? So this clearly we have seen here two methods of reducing alcohols to alkanes. One via dehydration and hydrogenation, the other, to form our tosylate, and then reduction with lithium aluminum hydride to form our alkane. For our tosylation of alcohols, this is a very important reaction in organic chemistry, which is why it's worth mentioning. So the hydroxyl group can be converted to a very good leaving group by converting it to a sulfonate ester derivative. That is, for example, p-toluene sulfonate esters or tosylate, as we just saw in the previous slide. And so the formation of the tosylate does not affect the stereochemistry of the alcohol carbon at all. The CO bond is not involved in the reaction, and so the reaction proceeds with retention of configuration. And so we have here p-toluene sulfonyl chloride, and we have our alcohol here in the presence of pyridine. We basically have replacement. Let me show you what's eliminated. So we replace the hydrogen here with hydrogen and the chlorine, right, to form our tosylate here. So we have a new bond between this oxygen and the sulfur seen here in the presence of pyridine. So we call this species a tosylate, right? And this reaction is very important because tosylate is a very good leaving group. So because substitution occurs via a SN2 mechanism, you have inversion of configuration results when the leaving group is bonded to a stereogenic center. So let's look at this example here. So let's say for example, we started off with an alcohol and we made this tosylate, then the cyanide group can attack from the back side and therefore causing the carbon oxygen bond here to break, and therefore you have inversion of configuration, right? So the tosylate here is it's an excellent leaving group. So if you want to get rid of an alcohol, you can tosylate it and then react it with the nucleophile that you want to replace it with, and note that it will happen with inversion of configuration. All right, so this leads us to our question 4, which says, show how you would effect the following transformation. So how would you go from an alcohol to, substituting an alcohol with our cyanide group here? Well, if you guessed that, okay, I could make my tosyl reacted with tosyl chloride in order to make your tosylate, and then react it with some cyanonucleophile in order to get the target molecule, right? So clearly we don't have a stereogenic center, and so that is not the focus here. We're just showing how we can go from one functional group to the next, starting with alcohol and replacing it with a nucleophile. So our follow-up question 4 says, give the product or products of the following reaction. So again, you have an alcohol, but this time it's thionyl chloride. So what is the product of this reaction? All right, so now we're going to look at ethers, and I think that's where we're going to finish it off for today. All right. So the structure and nomenclature of ethers. So organic molecules that contain a carbon-oxygen-carbon unit, as you know, we know them to be ethers. An oxygen atom with 2 alkyl groups attached and no hydrogen atoms on the oxygen, we call them ethers. So they're commonly used as solvents in organic reactions. You know, we're familiar with diethyl ether, THF. They resist chemical reactions, which make them good solvents. And they are not affected by acids or bases at moderate temperature. So great to conduct reactions. And so for the nomenclature, ethers are named by identifying the chains attached to the oxygen. And so the longer chain is the parent. The oxygen bearing the shorter chain is treated as a substituent. So let's look at a few examples here. Here, well, clearly here, there is no chain that is longer than the other. So it's methoxymethane. Here, this chain is longer than this one. And so this is the parent, and therefore the shorter one the oxygen bearing the shorter chain is now the substituent. So this is the substituent, which is why it's methoxyethane, sorry. And then here we have a 3-membered ring, which is longer than the methyl over here. So this is now the substituent, which is why it's 2-methoxypropane. And of course, this is the structure of THF, tetrahydrofuran, tetrahydropyran, and 1,4-dioxane. So how are these ethers prepared? Well, firstly, acid catalyzed dehydration of alcohols, or Williamson ether synthesis. So for the acid catalyzed dehydration of alcohols, so the alcohol in the presence of acid, you can get ether. It proceeds in 3 steps. So you have protonation, SN2 reaction, and then deprotonation. So I'm sure, looking at everything here, that you could come up with a possible mechanism. And it's a very important point to note here, that limited to the synthesis of symmetrical ethers, right? So if you want to make an ether that is unsymmetrical, you probably want to use another synthesis. All right, so here, how does it work? So here we have the first step, which is the protonation, right? So our alcohol is protonated, and I'm sure you would have guessed that. And then another molecule of alcohol now attacks the this electrophilic center here, and then breaks the carbon-oxygen bond, quenches the positive charge, and then this intermediate here would have a hydrogen present on the oxygen, and therefore it needs to be deprotonated. So another molecule of alcohol or water could pull this proton, quench a positive charge, and we end up with an ether. So this is the acid catalyzed dehydration of alcohols. And then we have our Williamson ether synthesis. So when an alcohol reacts with a base, the product is an alkoxide, for example, sodium ethoxide, right? And so alkoxides react with primary and secondary halides to form ethers in what is known as Williamson ether synthesis, all right? So we have our alcohol and we have our base in the form of sodium hydroxide, or hydroxide will do what bases do, pull a proton to form our alkoxide. And then once our alkoxide is formed, it can react with an alkyl halide. So again, another use for alkyl halide here to form our ether. So very simple, very intuitive mechanism to form our ether in the form of, well, the named reaction, Williamson ether synthesis. So for our reactions of ethers, we're looking here at the reaction with HX, right? So we have our ethers here, and in the presence of a strong acid like hydrogen iodide, which is a very strong acid, you can have cleavage occurring. And so the hydrogen ends up being attached to the oxygen, and the iodide ends up being attached to the methyl here. So essentially you have cleavage of this bond, right? This bond is cleaved, and then the hydrogen adds to the oxygen, the iodine adds to the carbon. Now it also works for cyclic ethers as well. So clearly this is symmetrical, so it doesn't matter which side, but you have cleavage nonetheless, right? And then the hydrogen adds to the oxygen, and then the iodine adds to the carbon. And the same thing happens here. You have cleavage and hydrogen, so we have an alcohol at one end and the iodine at the other end. And then finally, these are some examples. So cleavage occurring here, right here with hydrogen bromide. You also have cleavage occurring here to form our alkyl halide, and here another ether, we also have cleavage occurring here, right? So hydrogen is attached to this oxygen to form a phenol, and then the halogen attached to this carbon to form our alkyl halide. So pretty much similar to what we saw here. So that leads us now to our final question, question 5, which says, what happens when you combine hydrogen iodide with an ether? So simple question, right? So what happens? The ether bond is cleaved to yield an alcohol and an alkyl iodide. That is, if it is not a cyclic ether. If you have a cyclic ether, the ring will open as we saw, and one side of the ring would have the alcohol while the other end will have the iodine. And our follow-up question 5 is, discuss the Williamson ether synthesis. All right. So if you made it all the way to the end, congratulations, you stuck with it. And thank you so much for watching, and see you then.